Hello and welcome. Shadows in literature are often depicted as symbolizing mystery, hidden truths, and even ghosts. In science, shadows are considered as mere absence of light and so aren't really studied very well. But there are times when studying shadows can reveal deep truths. For one, consider the lunar eclipse. It is an event in which Earth blocks sunlight falling on the moon and casts its shadow on it. The ancient philosophers who were aware of this concluded that the Earth itself must be round, for only round objects can cast round shadows at all times. Yet another interesting use of shadows was done in ancient Greece by a philosopher called Eratosthenes, who by measuring the lengths of shadows in two different cities could calculate the circumference of the Earth. It is a simple calculation that we can ourselves do. Let's dive into it right away and understand how shadows can reveal not just the shape of the Earth, but also its size. As the Earth goes around the Sun, spinning on its own axis, every once in a while it so happens that at a particular time of the day, usually near noon, at some locations on Earth, the sunlight would be beaming exactly downwards. This would mean that in these locations, at those specific times, vertical objects like straight poles would cast no shadow at all. This is observed as no shadow day. As observed from Earth, this would mean that the path of the sun across the sky would pass exactly over your head at somewhere close to noon. And the instant at which the sun is exactly overhead, shadows would disappear. Now, this should not be confused with an actual magical disappearance of shadows. It's just that because the sunlight beams vertically downwards, any straight object would cast a shadow in exactly the spot right beneath its foot, and hence the shadow would not be visible. And this phenomenon lasts for just a few seconds, for as the Earth continues to spin, the position of the sun shifts continuously, and the sun would very soon pass the point that is exactly overhead. Also, because the Earth's surface is not flat and the Earth's rotational axis is tilted, no shadow days are observed only from specific locations on a specific day of the year. The sun does not pass exactly overhead every noon, and certainly not everywhere. Basically, for you to experience the no shadow moment, you, the sun, and the center of the Earth must all be aligned along a straight line. If you're in the wrong location or at the wrong time, you wouldn't experience no shadow. Like I mentioned earlier, the no shadow occurrence, besides being fun, also can reveal to us the size of the Earth. To understand how, consider two cities. Let's call them City A and City B. Let's say the distance between the two cities is X kilometers. By distance, I mean the length of the straightest possible line drawn between the cities. Let's say it so happens that on a particular day, it is no shadow day in City A. Then on that day, if City B is sufficiently far away, it wouldn't be a no shadow day there. In other words, while vertical objects cast no shadow in City A, at that same moment, vertical objects would be casting some shadow in City B. To carry out measurements, all one must do is have a friend in City B and ask them to measure the length of the shadow cast by a vertical object, say a pole, and also the length of the pole itself. Let's say the length of the pole is h and the length of its shadow is L. But these measurements, especially of the shadow, must be done at precisely the moment it is no shadow in City A. Once we have this length, it's a matter of using simple trigonometry to figure out the angle made by the sunbeams with the vertical pole. That is, compute tan of theta, and from that we can compute the angle theta itself. Now, from geometry, it turns out that this angle theta that we just computed must be the same angle made at the center of the Earth when arc joining the two cities. What we essentially have is a sector of a circle with radius equal to the radius of the Earth, angle theta at the center, and the arc length AB, which we have labeled x here, the distance between the two cities. Then it's just a matter of using one more formula from geometry that links the arc length to the angle. R equals x over theta. And from this we can compute the radius of the Earth. Once we have the radius, we use the formula c equals 2 pi r to compute its circumference. And Eratosthenes did these calculations and found the circumference of the Earth to be about 40,000 kilometers, which is almost exactly the currently known value. There are some uncertainties involved in his calculations, especially because he used an ancient unit of length, stadium, rather than the modern mile or kilometer. But we can be sure that he was extremely close to the true value. And this was done in about 200 BC. No advanced technologies or even advanced mathematical calculations required. A high school student can easily perform these calculations. And that's an ingenious technique, and it is one that we can employ today too. Even though we know the precise circumference of the Earth today, isn't it so much fun to figure it out on your own and see if you got a value close enough? After all, how often can one claim to have measured the size of the Earth, and that too with mere shadows?